In the realm of science, certain names resonate through time, forever etched in the annals of history. One such name is Weibull, a Swedish engineer and mathematician whose work revolutionized the way we understand and predict failure. Born in 1887, Weibull dedicated his life to unraveling the complexities of material strength and the seemingly random nature of failures. Little did he know that his quest for answers would lead to a groundbreaking equation, now known as the Weibull equation, that would transform industries worldwide. Weibull's journey began in the early 20th century, a time when engineering was grappling with the limitations of traditional statistical methods. The existing models struggled to accurately predict the lifespan of materials, particularly in complex systems with numerous components. Engineers needed a better way to understand the probability of failure over time, a tool that could account for the variability inherent in real-world materials and operating conditions. This is where Weibull's genius shone through. Weibull's breakthrough came from his deep understanding of statistics and his keen observation of real-world phenomena. He recognized that failures often followed a pattern, albeit not a simple linear one. He observed that the probability of failure was often higher in the early life of a product, decreased over time as the product stabilized, and then increased again as the product aged. This pattern, he realized, could be described mathematically, and thus, the Weibull equation was born. The Weibull equation, in its elegant simplicity, provides a powerful tool for analyzing and predicting the lifespan of everything from aircraft components to light bulbs. It is a versatile tool that can be applied to a wide range of fields, from manufacturing and engineering to healthcare and finance. But what makes the Weibull equation so special, so enduring in its relevance? The answer lies in its ability to capture the essence of failure, to quantify the unpredictable. At its core, the Weibull equation is a probability distribution function. It allows us to calculate the probability of a component failing at a given time, based on a set of parameters that describe the failure characteristics of that particular component or system. These parameters, known as the shape parameter and the scale parameter, provide valuable insights into the nature of failure. The shape parameter, often referred to as the Weibull slope, determines the shape of the distribution curve. A shape parameter less than 1 indicates that the failure rate decreases over time, suggesting early failures are more likely. A shape parameter equal to 1 represents a constant failure rate, while a shape parameter greater than 1 indicates an increasing failure rate over time, suggesting wear out is the dominant failure mode. The scale parameter, on the other hand, represents the characteristic life of the component, the time at which 63.2% of the components in a population are expected to have failed. The ability to predict failure rates is paramount in many industries, but it is particularly crucial in aviation. The safety of passengers and crew depends heavily on the reliability of aircraft components, making accurate failure prediction an absolute necessity. This is where the Weibull equation takes center stage, providing a robust framework for developing effective maintenance programs. Prior to the widespread adoption of the Weibull equation, aircraft maintenance relied heavily on time-based schedules. Components were inspected or replaced at fixed intervals, regardless of their actual condition. While this approach offered a degree of predictability, it was inherently inefficient. Components were often replaced prematurely, wasting valuable resources, while others might have failed before their scheduled maintenance, potentially compromising safety. The Weibull equation revolutionized aircraft maintenance by enabling condition-based maintenance, a proactive approach that focuses on predicting and preventing failures before they occur. By analyzing historical failure data using the Weibull equation, engineers can identify patterns and trends in component failures, allowing them to develop customized maintenance schedules based on the actual condition of each component. This not only enhances safety, but also optimizes maintenance activities, reducing downtime and operational costs. The impact of Weibull's work extends far beyond the aviation industry. His equation has become an indispensable tool in reliability engineering, shaping the way we design, manufacture, and maintain everything from cars and bridges to medical devices and power plants. His legacy lies in his ability to transform complex statistical concepts into practical tools that empower engineers and scientists to make informed decisions about reliability and risk. Today, As we venture further into the realms of artificial intelligence and machine learning, the Weibull equation continues to play a pivotal role. Its ability to model complex failure patterns makes it an invaluable asset in developing predictive maintenance algorithms, enabling us to move from reactive to proactive maintenance strategies across a wide range of industries. The future of reliability engineering is undoubtedly intertwined with the enduring legacy of Weibull, the Swedish genius who dared to crack the code of failure. Thank you for watching this deep dive into the life and legacy of Weibull. If you found this video insightful, don't forget to like, subscribe, and hit the bell icon for more content on the unsung heroes of science and engineering. Special thanks to our partner, Tailwind Systems, for their unwavering support in bringing this story to life. Stay tuned for more fascinating stories that bridge the gap between innovation and humanity. Until next time, keep exploring, keep questioning, and keep pushing the boundaries of what's possible. Credits to Tailwind Systems, connecting technology, innovation, and skills beyond international borders.